Welcome back to ECE 320A. Homework 4 and 5 are due at the end of the day that we meet next, which is Tuesday. Sunday is homework number 4. Homework 5 is on Tuesday. Your second exam is a week from today. That got your attention. Exam number 2 is in a week, and I want to finish up chapter 12, and that means that we have a fairly long list of goals, but I've postponed one of those to the bottom because you don't necessarily need that to finish up your homeworks, but I think you do. I would like to finish up case 2 of the partial fraction expansion. We were working through many different ways or methods for finding coefficients associated with higher powers of factors in the denominator, and we'll look at one more of those. Then we will jump into poles and zeros of transfer functions and look at final value theorem and the initial value theorem. Those theorems are useful because they allow you to not have to inverse Laplace transform in order to find some of these limiting values, some of these limiting variables or values. And then we will return to the partial fraction expansion. If you don't like complex numbers, you can inverse Laplace transform in other ways, and that's what we will talk about in this last goal, is doing partial fraction expansion when we have complex roots, but we will use real numbers to do that solution. As a result of that, it hopefully will convince you that these two bottom equations are equivalent. You can show that if you have sines and cosines at the same frequency, you can combine those into one sine or one cosine, and typically in this book we will convert those into a cosine. That simply means now that we have a cosine obviously of the same frequency, but now it's shifted in time. It has an advance or a delay if we had both a cosine and a sine term. What is theta raised to? That's a degree. So that's in degrees. The other one, I did that because beta t is usually in radians. And so I was trying to indicate that if you're doing the inverse tangent, or if you found theta and it's now in degrees, if you are actually evaluating the argument of that cosine, you'll need to make sure that you're either in radians when you perform the cosine function, or both values are in degrees. You can't be adding radians and degrees. One will swamp the other, or give you an error, basically. Let's now return to where we were before, which was partial fraction expansion. And last time we had gone through all of these different methods except for the one that is starred. We looked at when we had repeated roots, that's case 2. Case 1 is when we have distinct roots in our partial fraction expansion. No x's on top of each other in the complex plane. In case 2, here we can have different or repeated roots, poles on top of each other, and we talked about using a convenient value of s, which can't be a pole value. That's what we mean by convenient. And convenient is, it might help your algebra if you select it conveniently. Then we looked at another approach that's a limiting expression approach or technique. We multiply both sides by s and let s go to infinity. Then we put everything over a common denominator and equated coefficients of like powers of s. Now we will look at the technique that's actually discussed in the textbook, which is the differentiation approach. And here it is. It's a nice, clean formula. Maybe not. But Suppose that we have an nth order, a Nevada order root. So we have P naught, or poles at s equal minus P naught, and that's now repeated n times. N could be 10. On the exam, it'll probably be 15. Just saying. Teasing, teasing. Little n probably won't be more than 4. Or we might have a problem. We might have an emergency. So here is the formula. And you now know here I'm, just for illustration purposes, I'm concentrating or I'm restricting this example to only having poles at minus P naught. But you could have other poles that have distinct or that are distinct, and you can still do the same thing. It's just you have to incorporate those in the analysis. Here I'm assuming that capital F of S is strictly proper. That's what that parenthetical degree of capital N being less than n means. That just means that we have a strictly proper transfer function. And don't forget that we have many, many more terms depending on how big little n is, and that just continues down to a sub n over s plus p naught raised to the first power. If we order the partial fraction expansion coefficients, or the residues, consistently with how I've labeled this or set this partial fraction expansion up, then each of these a sub l's you can find using the formula at the bottom of the page. And that red vertical line just says we are evaluating the result at that pole location, just like we've done in the past. But now, because it is repeated, we actually have, or we can find these coefficients using this technique, which means that now, instead of maybe solving multiple sets of equations, we can solve them one at a time, but now we just have to perform this differentiation with respect to s. For example, if we looked at a sub 1, the coefficient on top of s plus p naught to the n, how many times do we have to differentiate things to obtain that a sub 1? None. And that's what we have done in the past. We said, oh, if we are looking for the coefficient on top of the highest powered factor, we don't have to do anything fancy. That's like we've done before in the distinct pole case. And that's what this formula actually simplifies to, 1 over 1 minus 1. And how, now we have to remember that 0 factorial is 1. And d to the 1 minus 1, so we're not differentiating in that case. But for the other cases, we are. And that's true then if we go up to Nevada or little n of 10 or 15 or whatever you have in front of you for the number of poles that have been repeated. So that's d. So this is just telling you how many times you're having to differentiate. And why did I put that there? Is that what you're saying? This doesn't normally go in there, does it? Yeah, it does. Wake me up. Ask me another question and I'll fall back asleep. It just looks weird, doesn't it? But it's usually the third or fourth derivative is in that formula. Okay, let's apply that to this example. Suppose we have capital V of S, and V is generic. That could be a current, it could be a velocity, it could be a voltage. We're just saying here is a given transform, and can we immediately start doing or performing the partial fraction expansion on that? So you had a 50-50 chance if you were flipping a coin, but I think most of you said yes, and the reason you said yes, it's strictly proper. The numerator is second order, the denominator is fourth order. Now if I start with the s plus 2 terms, and if I try to make this consistent with the way that the formula was set up before, what does the partial fraction expansion look like for this particular problem? So now how many terms am I expecting on the right-hand side? 4. So if you don't do anything else on an exam, do that and you might get a point, right? You know there's 4 terms, and now you can show that to me. And you could say, oh, I have s plus 2. Let's start the way that we had before. And now let's say that's a sub 1. Now what's my next one? Now we need to start decreasing the power on that repeated root factor. And we keep going until we are down to the power of 1. And then we can stop, and now we have a sub 4 over s plus 1. Questions on that? Now, which ones can we find immediately? Which of these 4 coefficients can we immediately compute without too much effort? A1 and A4. Let's do A4 and then we'll come back to A1. A4 is just going to be s plus 1 times v of s, evaluated at s equal to minus 1, which is now s squared plus 3s over s plus 2 cubed, evaluated at s equal to minus 1. I'll let you do the math. That ends up being minus 2. Then A1 we can do exactly the same way because that's associated with the highest power of the repeated root. It's just now we need to make sure that we evaluate that at the root itself, which is minus 2. And that now simplifies to s squared plus 3s over s plus 1, evaluated at s equal to minus 2, and that one actually ends up being 2. So 2's are wild. And it's not 4 and 1 now, is it? Good. We've broken away from that pattern. Now, how can I find a sub 2? A sub 2 I should be able to find using this formula. That's the whole point of this example. Let's now plug in little l equal to 2, and we're going L equal 1, 2, up to Nevada equal to what? Now we can do some hand signals, right? 3. So a sub 3. A sub 2 is now going to be 1 over, and I'm going to go ahead and write all of this out so that you see how that works in the expression. And this is now s plus 2 cubed times v of s, according to this formula. Little n doesn't change, does it, as we index through L? Little n stays at 3. And if we hit v of s with s plus 2 cubed in the numerator, that cancels, and we're left now with s squared plus 3s over s plus 1. And we need to differentiate that 2 minus 1 times, and then evaluate that at s equal to minus 2. Now, do you remember your quotient rule for differentiation? Okay, I have a few years on you. I don't, so I always just use the product rule. That's easier for me to remember. I don't know why, but it is. Okay, so now let's take the derivative of the numerator. Well, no, I said I was doing the product rule, didn't I? So let's consider we have s squared plus 3s as my first term, and s plus 1 raised to the minus 1 is my second term in this product. So I'm going to say the derivative of the first, which is 2s plus 3, and there's s plus 1 to the minus 1, times the derivative of the second times the first. And the derivative of the second is minus 1 times the first, and then we have s plus 1 to the minus 2 times the derivative of s plus 1 with respect to s, and that's just 1. So maybe that's confusing, that minus 1 there. But now I need to evaluate that. You differentiate however you want. You use whatever technique you want to use, and this, if you evaluate it, ends up being 3. Now, to help with the next coefficient, I'm going to go ahead and combine these, get those over a common denominator, which is s plus 1 squared. And my numerator becomes s squared plus 2s plus 3. And now I will differentiate that, meaning a sub 3 is, from the formula, that's 1 over 3 minus 1 factorial d to the 3 minus 1 over ds 3 minus 1, or differentiate twice, this s squared plus 3s over s plus 1. But we've already differentiated that once, and that's what's in red, so I'm just going to have to differentiate once what's in red. Is that making sense? Question?
Yeah, when we went back to the topic of A2 differentiation, why are we not multiplying that by
S plus 2 squared. So here, if we look at this, we should multiply whatever we're trying, or whatever was on the left, which is our v of s, here it's f of s, by the factor raised to the highest power. And in this case, our highest power was 3. So now, by multiplying v of s by s plus 2 cubed, that denominator factor is gone. And this is what's left over. Does that help? And then I simply differentiated that once with respect to s. And I ended up with what's in the square brackets. I actually simplified that, or put that over a common denominator, but before I did that even, I could have evaluated it at s equal to minus 2. Whatever way you want to do it, you end up with 3 for a sub 2. A sub 3 now is going to be the same thing that we started with, which is the s plus 2 cubed times v of s. We'll differentiate that twice, but we already differentiated it once, and that gave us the red. So why don't we just differentiate the red once to find what we need in a sub 2, or I'm sorry, in a sub 3. Now we can say that a sub 3 is 1 over 2 factorial, and that simplifies, isn't it? 2 factorial is just 2. Then we differentiate once what I said was in red, and that's s squared plus 2s plus 3 over s plus 1 quantity squared. And once we do that, we will evaluate that expression in square brackets at s equal to minus 2. If we do the differentiation like I did before, I'm going to pull out the 1/2, and now I differentiate the numerator term with respect to s, and that's 2s plus 2. And that's then multiplied by the second factor, which is just the s plus 1 to the minus 2. Then I need to differentiate the second term, which is what I'm considering to be s plus 1 to the minus 2. So that now gives me minus 2 times s plus 1 raised to the minus 3 times the derivative of s plus 1 with respect to s, which is 1, and all of that needs to keep the first term in place, which was s squared plus 2s plus... Again, if that is not looking familiar or comfortable, just do it how you want, differentiate it how you want, and hopefully you will get the same answer that I ended up with, which I told you 2's were wild. Now, what's the structure of the solution going to be? What is v of t? We now have all of our a's. We have a1, a2, a3, and a4. In terms of a1, what's that first term going to look like when we take it into the time domain? So that's now in a1, but now we have to divide by this factorial term, which is 1 over 2 factorial. I'm going to write the factorial just so that you know that it's not just 2. It is just 2, but it's 2 factorial. Then it's t squared, e to the pole was at minus 2, and that's the first term. Then we have the second term, which let's not even mess with 1 factorial, but that's what we're dividing by. This is now t, e to the minus 2t. Then we have an a sub 3, e to the minus 2t, plus an a sub 4, e to the minus t, and that's valid for non-negative values of time. And that's the inverse Laplace transform, and we could plug in the a's, a sub 1, 2, and 3, since we just calculated it, but I wanted to show you where those sit relative to some of these other scaling factors, the 1 over 2 factorial, etc., so that you know where those come in. Yes?
So the 1 over 2 factorial is based off the fact that we had s plus 2.
Yes, so the 1 over 2 factorial is a result of having that factor cubed in our partial fraction expansion. If it was to the fourth, then we would have 1 over 3 factorial t cubed, scaled by whatever it is, a sub 1, if we were starting at that. Questions on that example? Yes? Well, in this case, what did we use? We used the question was how long or how much do we have to use this differentiation method, I think. Is that the question? You use it until you don't want to use it anymore or until you get what you need out of it. I wouldn't use it more than you have to. If you want to use a limiting expression, if you want, you can use these in combination to try to make your life a little more easy. Question?
Yeah, when would you want to use this?
When? Personally, I seldom use this, but I wanted to present it since it's in the book, because we typically don't have too much in terms of powers of a repeated factor. We don't have poles on top of each other too much, but if you do, if you wanted to not have this complicated, let's say, set of equations to solve, and you like to just chunk through then and get these equations individually, or these coefficients individually, then this would be the technique to use. If you wanted to use your calculator to do the differentiation, then maybe this technique isn't that ornery. Now, you want to thank your gift giver if you actually have something to this effect. If you look at doing what we just did and you plug it into one function called expand, and you say s squared plus 3s, that's the numerator, and I go crazy with parentheses just so I know that it's putting things in the right spot. Here's a parenthesis, then it's s plus 1 times s plus 2 cubed. Wow. Good thing I'm typing that into the calculator and not having to draw it in. Then that needs to be inside the expand function, and now your calculator will dutifully say something like 2 over s plus 2 plus 3 over s plus 2 squared. Now everybody's getting out their calculator, all right. S plus 2 cubed minus 2 over s plus 1.
They shouldn't even take the test.
So you're allowed to use the calculator, but I'm going to try to design the exam so that it's not going to be that much benefit to have it, but if you've got it, you might as well use it. But you need to say something to the effect of from the calculator. And don't just say, here it is, because I'll assume you were looking somewhere else and not your calculator screen. It was a neighbor. So here, in terms of the formulas, this is now two inverse transforms. And that's now what v of t looks like when we plug in the actual coefficients, where this coefficient was actually 2 over the 2 factorial. All right, now that I've stirred you up, let's go back, or go to something new, okay? All right, in years past, 80% of the class had those calculators. Now Dr. Marsland's programmed your calculators to do something that's kept you from buying those more expensive, which is good, but that's a new twist on this material. Question? Pardon? It doesn't, you would have to check this out, but when you have complex roots, it bongs. So check out my videos on YouTube for the complex roots. But even those aren't repeated. But you have to kind of be, clear on how you're using your calculator, if you have one. Now, let's move on and talk about poles and zeros. Suppose that I give you capital X of S, just to give us something to think about or to discuss, where the numerator is s squared plus 4s plus 3, the denominator is s cubed plus 9s squared plus 33s plus 65. And the numerator factors, as does the denominator. We can factor out a 5, and then we're left with a quadratic of s plus 2 squared plus 3 squared. And I'm going to refer that, or to those polynomials, as the numerator polynomial capital N and the denominator polynomial capital D. But I hope you already see the time domain structure of what you would have if you take the inverse Laplace transform of capital X of S. What kind of terms do you see in little x of t? So now you have an e to the minus 5t piece, and what else do you have? Where are the roots of that complex factor? Minus 2 plus and minus j3. So what does the 3 give you? It gives you the shaking. It gives you the frequency of 3 radians per second. And what does the minus 2 give you? That's the e to the minus 2. In general, you could say, okay, I have e to the minus 5t with some weighting plus some other weighting e to the minus 2t cosine of 3t plus another weighting e to the minus 2t sine of 3t, and you're done. That's the structure of your answer. And you know that just by factoring the denominator. What we want to do now, though, is introduce more formally what I've been mentioning already, and that is this concept of poles and zeros. Let's start with zeros. Here we're going to say that the values of S that cause capital X of S, that's the whole thing, to equal 0 are called zeros. That seems kind of logical, doesn't it? Now, here if you want, well, let me write the next thing and then I'll tell you why I'm making the distinction. Also, values of S that cause the polynomial, capital N of S, which is equal to the numerator of capital X of S to equal 0. If we wanted to get a little bit more specific, those are called finite zeros. And those are the ones we usually think about when somebody says the zeros. Now, what's the difference between the blue line and the black line? Or blue sentence and the black sentence? So here we're talking about zeros, and now, are there other values of s that are not finite that cause capital X to vanish or to equal 0? What's the difference between the order of the denominator and the order of the numerator? What's the order of the denominator? The highest power of s, if you multiplied that out, would be, well, we already did it, right, before it was factored. S cubed. The order of the numerator is 2. So in this case, you could have an s going off to infinity that would cause capital X of s to be 0. Do you see that? You have 1 0 at infinity. And you have how many finite zeros? 2, which is how big your numerator polynomial is in order. So you have 2 finite zeros and 1 0 at infinity. But we don't usually mess with zeros at infinity. But if somebody starts talking about zeros at infinity, you don't go off into la-la land. You know what they're talking about. Question?
On the test, will there be anything that we need to factor like this? Like what?
On the test, will there be anything that we need to factor like this? Probably not. What I will do is I may factor it into a product of quadratics, but you'll be responsible for determining if that quadratic is complex roots or real roots. Is that okay?
Yeah, that's fine.
But if it's fifth order, I will give you a factored form of that fifth order as maybe 1 real and 2 quadratic, but those 2 quadratic could both have 2 real roots. So you could have 5 distinct real roots in that denominator, but you would have to be determining that. Is that clear? Because your calculator can factor that. It can do C factor, and C factor will factor complex polynomials if you have the right calculator. All right, there you go again. All right, so now let's continue. Now, I think I've... Where are the finite zeros? If I can have your attention back from la-la TI land, it totally does, doesn't it? Yes. Where are my finite zeros? -1 and -3. Let's now sketch those. So I have a 0 at -1 and a 0 at -3. This is the S-plane, and now here, this is going to really stretch our imagination. I use open circles for zeros. So I'm going to put an open circle there and an open circle there. Now, we want to populate some X's on that. We're playing a game here. We have X's and O's. The O's are zeros and the X's are poles. So, now let's introduce the concept of poles that I've already talked about. The values of S that cause the transfer function or the transform, capital X of S, to become infinite are called poles. Or we can say that another way. Now we can concentrate on the denominator polynomial. We can say values of s that cause the denominator of x of s which we've now labeled as capital D of s to equal 0 are called finite poles. We usually don't use the finite adjective. And in this particular example, what are the poles? We have one at -5, and then we have the other two at -2 plus and minus j3. And we can now go back and put those into our diagram, and we can say we had a -5. These are now the x's. And we had a -2 plus and minus j3 and a -2 minus j3. What influences the structure in our time domain answer? X's, O's, or combination? What influences the structure of our expression for little v of t? Just the x's. The zeros influence those coefficients that you find when you do the partial fraction expansion. The poles give us the structure. So I could give you a pole zero diagram on the exam, and I would hope that you could then give me the structure of the solution. If I say, okay, capital V of S has the following pole zero diagram, and I give you that with X's and O's. And then I say, what's the structure of little v of t? And that's what I was asking for a minute ago, but if I just gave you that, now you would simply have to focus on the x's, and the real parts of those give us the decay, e to the minus 5t, e to the minus 2t, and the distance, the vertical displacement, gives us the shaking, the frequency, and the cosines and sines. Anytime we have complex conjugate poles, we have sines and cosines. And if they are off of the imaginary axis, they're damped. They're exponentially damped sines and cosines. If they were right on the imaginary axis, they never decay. There's no e to the minus, there's an e to the 0t. They're just shaking. You hit it, you get it started, and then it just oscillates. If you had an oscillator, you would have poles on the imaginary axis. If you had x's in the right half plane, what's going to happen? It's going to go up, and we might have a fire truck coming up to rescue you. It might burn up. You might smell it burning. It might go poof. If you're lucky, that's all it does. But if it's in the right half plane, then you have these e to the 6t, e to the t. Those are going unbounded with time. Is that clear? We want to have things in the left half plane, these x's, the poles. Is it the same for zeros? So do the zeros influence the stability of our response? No. They influence the coefficients that weight our structure. And if we have zeros in the right half plane, they make your system a little bit more problematic, let me just say that. They're non-minimum phase zeros, and if you take a controls class, systems that have non-minimum phase zeros, or zeros in the right half plane, are more difficult to work with. They kind of like to, if you were, so a bicycle has a right half plane 0. You want to go left, you kind of go right first and then you go left if you're making a quick maneuver. You didn't know your bike. And the bike is what? You probably have your poles. That's an inverted pendulum, isn't it? If you're not moving a bicycle. It's kind of hard to stay, although this morning as I was driving in, I saw somebody at an intersection and he was impressing me. He was stopped, but he was trying to keep his bike upright. And he was doing a decent job of it, but I kept seeing the crosswalk light 10, 9. I go, I wonder, I couldn't see him in my rearview mirror to see if he made it for the duration of the time that he had to try to take a left. All right, what is little v of t? Oh, you're answering, or you have a question?
So, when we have the imaginary part of everybody, where we always have a plus or minus imaginary part.
Did everyone hear that question? When we have imaginary pieces to our poles, are they always going to come in pairs? Here there's a pair, a left and a right, an up and a down. Yes, if we have what? If we have real coefficients in our transform. If you allowed complex coefficients, then you could have them in isolation. But most of our designs in the real world, we're going to have real coefficients. Those come then, or those complex poles or zeros come in conjugate pairs. Other questions? Now, with this blue and black diagram, what's little v of t if this is corresponding to capital F or capital V of S? What's the time domain structure based on that pole zero diagram? Structure, we have to include some coefficients, so let's just say in A1, we're not asking for what that is. That's going to be determined by the zeros, where they're located, and I'm not asking you for those. But we had a pole at -5, and it was real. And we just have this exponential term. Then we could write it as k e to the minus and there's many different ways you could write it. You could say, okay, cosine, let me call this a k1, of 3t plus a k sub 2 e to the minus 2t sine of 3t, and that's there. Or we could say a1 e to the minus 5t plus, let's say, b e to the minus 2t cosine 3t plus theta. That's equivalent. If I ask for the structure, the black or the blue is correct. Either one. And we're going to show, if we don't run out of time, which I'm looking like we might, I'm going to show the equivalence of those. But before we do that, I want to get into the theorems. I'm not going to prove them today. We'll just use them today. The initial value theorem and the final value theorem. Yes? What happened to the zeros again? The zeros are going to make their impact on those coefficients. Those coefficients will be influenced by the zeros. The structure of the response, though, is influenced by the poles, and that now gives us the structure of our response. The zeros, so in this diagram, that's why if somebody gives you this pole zero diagram and they say, what's the structure of my response, you don't really have to worry so much about the zeros. You just take the poles and go into the time domain. with these yet to be determined coefficients. Let's now talk about these theorems. And the reason we're interested in this is sometimes we're only interested in the initial value, let's say the initial voltage, the initial current, or the final value of the time function. And these theorems actually are designed to save you work. So just like your calculator can save you work, these theorems do also. These theorems allow us to avoid, or avoids performing, the detailed inverse Laplace transform. We don't have to find f of t, little f of t, if we don't have to. But on the exam, you'll need to in some cases. But here I'm going to say avoids performing complete inverse Laplace transform. That's the beauty of these, and we're now going to present the the initial value theorem and the final value theorem. Let me state the final value theorem. That's usually the one that we focus on, or if we only have time for one, this is the one that I would give you, but we'll get to the other one, I hope. Final value theorem. If we have two conditions, if the time domain waveform x of t and its derivative x prime of t have a Laplace transform, and I'm going to say that by saying are Laplace transformable, and now you could think of those x's, or your signal being well behaved, which is basically most practical waveforms that you're going to be playing with are well behaved. So this one we usually just sort of assume that x and x prime are Laplace transformable. Now I need more space. Let me just say and. Here's the one that you really need to worry about. S, x of s, so now we're multiplying the transform, capital X of s, pre-multiplying it by little s. That expression has no poles, and now we know what poles are. On the j omega axis, or in the right half plane, so we are focusing on condition 2. We check that. If that's satisfied, then we can find the limit, the limiting behavior of our time domain waveform. So now we're looking at the limit as t goes to infinity of little x of t is now equal to the limit as s goes to 0 of that expression that we just computed. S times capital X of s. And we didn't have to inverse Laplace transform capital X of s in order to find little x of t. We can just apply this limiting argument. Yes?
That poles, can they have a J element to them? Or can they just not be a J vector axis?
The poles cannot live on the imaginary axis, and they have to be in the left half plane. They can't be in the right half plane, and they cannot be, but they can have an imaginary component. They can shake, but if they're in the left half plane, that means there's some exponential decay. Let's look at some examples of applying this. Suppose we have example 1 given as capital V sub 0 of s is now minus 4 over 2s squared plus 3s plus 1. Now, instead of factoring that denominator, I'm going to just factor out the leading coefficient and make it monic. I'm going to factor out the 2, and now I have s squared plus 3 over 2s plus 1/2. Is everybody comfortable with that? Now, before you pull out your calculator or perform the quadratic formula or apply the quadratic formula to find the roots of that, let me let you in on a fact. Do you know if this polynomial, where its roots are located? Are they located in the right half plane or the left half plane, or are they on the imaginary axis? Can you tell by just looking at that? They're in the right half plane or the left? Somebody got a coin? Let's flip that coin. These are actually in the left. The reason, okay, so let me just say that. The roots of this, and may I abbreviate that to be LHP, because I know you're tweeting this lecture. So now the roots are in the LHP, the left half plane, and the reason is, what's the order of that polynomial? It's second, or it's a quadratic, and this is the only reason why this is okay, is because it's a quadratic polynomial, and the coefficients of the s1 and the s to the 0 are both positive. Because of that, we know, boom, it's in the left half plane. So it's quadratic, and 3/2 is greater than 0, and 1/2 is greater than 0. And since the roots of my denominator are in the left half plane, where are the poles of V sub 0 of s? Or, if I even wanted to say that, the poles of, in our formula, we need s, the poles of s V sub 0 of s. So if I now multiplied this by s, where are the poles of that? They're in the same location as the roots of that denominator, aren't they? So the poles of s, V sub 0 of s, are, and I'm going to say that means if they're in the left half plane, they're stable. And that means they're in the strict left half plane. Which says then that I'm going to be able to apply the final value theorem to find out where is little v sub 0 of t going as t goes to infinity. Now I can say the limit as t goes to infinity of little v sub 0 of t is the limit as s goes to 0 of s v sub 0 of s, which is the limit as s goes to 0 of minus 4s over 2 times s squared plus 3/2 s plus 1/2. And what happens when I let s go to 0? What happens in the numerator? That goes to 0, doesn't it? If I let s go to 0 in the numerator, what happens in the denominator? I now have 2 times 0 squared plus 3/2 0 plus 1/2. That's going to be 1, which is 0, which says that that particular transform in the time domain is going to go to 0 at infinity. And what's infinity in this case? 5 tau. And it's definitely not way, 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 way off there in time, is it? If you looked at the roots of this, you would find that they're at, if we did the roots of this quadratic, it's negative b minus 3/2 plus and minus square root of b squared minus 4ac over 2a. So it's minus 3/4, I think, for the real part question.
Yeah, how do we know that, like, what would we know if it's not?
So here, the question was, when do we know that condition 1 is true or satisfied? We're not going to concern ourselves with that. We're working with well-behaved or practical or real signals. We're going to just assume that that's always the case in this class. It's only when you start getting e to the t kind of waveforms that this kind of goes crazy. And we're not worrying about that for this class. So why did I factor out the 2? I just wanted to, so my technique for finding whether those poles or those roots are in the left half plane is based on a polynomial being monic. And then I just have to focus on the s to the 1 coefficient and the s to the 0 coefficient, those 2 coefficients. Meaning the leading coefficient could have been a minus 2. I would need to factor that out and then worry about those coefficients that are resulting or that are remaining. All right, let's look at example 2. Wow. This lecture is going unstable. Capital X of S. No. 6 s plus 1 over s squared plus 1.5 s plus 0.4. That's my capital X of S. Now, I went through a lot of discussion in the last example, but now let's go a little bit quicker. Is this going to have will we be able to apply the final value theorem to this capital X of S? Why? We need to be worrying about the poles of S, capital X of S, right? This will cancel, so we're not going, and we know that this is positive and that's positive. That's what we need to conclude that the poles of S, capital X of S, are in the left half plane. The fact that we started with one pole at the origin, that actually gets canceled by the S that we pre-multiply by when we're looking at S, the poles of S, capital X of S. Let me now get rid of this so that if you go back through the notes, you're going, well, what? All right, so now we have capital X of S. Let's now look at what little x of t does in the limit as t goes to infinity. That's now the limit as s goes to 0 of s x of s. That's now the limit as s goes to 0 of 6 s plus 1 over s squared plus 1.5 s plus 0.4. Meaning I've already canceled the s in the denominator expression. Now let s go to 0. What do I end up in the numerator with? 6. What happens in the denominator? 15 is where I end up with my final value of x. And infinite is not very long in electrical engineering. The final value. We reach 15 pretty quick. What about the next example? What I want to do now is sort of put on the brakes, meaning you don't want to just try to apply the final value theorem. Let's do the final value theorem quickly. Question.
So 15, that representing the value of the function.
So,
How is that time?
so now this 15 is what the inverse Laplace transform of x of t would be when you let t go to infinity. So after all transients have died out or gone away, your little x of t will approach 15. It will be 15. That's the final value. Did that answer your question? Question?
Yeah, are we just thinking like as time goes?
You might be wanting to know, maybe I'm designing something and you go, oh, based on this circuit that I've built, what's the final value if I put in a step of 6? Then you don't have to inverse Laplace transform. You can inverse, or you can do the final value theorem and you can say, oh, I'm going to 8. Okay, that's okay. What's this one going to do? Can we apply the final value theorem? Or maybe I should ask, should you apply the final value theorem to this? Where is this pole located? This is a right-handed pitcher. This is in the right half plane. Sorry. The World Series, no, it's not quite the World Series, is it? But we have some RHPs and some LHPs. We want left-handed, or I'm sorry, left half poles. Does that mean that we can apply the final value theorem? If we looked at S, Y of S, where are the poles of that? Where are the poles of S, Y of S? They're at 1. What's that look like? If I inverse Laplace transformed this function, you should be able to do that now. What is little y of t? That's straight from the table, isn't it? That's e to the plus 1t, is it not? For t greater than or equal to 0. What's the final value of that? It might burn up, right? It's unbounded. There is no final value. So you can't expect the final value theorem to work on this. If you blindly applied the final value theorem, if one would have applied the final value theorem, then what would we end up with? We would say, oh, good, I can do the final value theorem. He wants to know where we're going. Limit as t goes to infinity of y of t. Okay, that's the limit as s goes to 0 of s y of s. I'm talking to myself on the exam, and you'll want to be kind of quiet. Limit as s goes to 0 of s over s minus 1. Oh, good, that's well behaved. 0. Good. But is it correct? No. You can't apply it. So if you this is, an incorrect result, you couldn't apply the final value theorem because when you check the second condition, S, Y of S, the poles were in the right half plane. Boom, I can't apply the final value theorem. If you do, it will give you the wrong answer. Questions on that? So we shouldn't have gone down below the blue, the Y of t. Let's look at another one. Suppose now I give you the following. I say capital Z of S is 2 over S squared plus 4. And I ask, what's the final value of little z of t? You're now immediately starting to look at this, are you not? S times capital Z of S. And saying, okay, where are the poles that I have if this is the case? And I might give this to you on the test. I might give you a quadratic. So now you're interested in this. And what do you want? In order to apply the final value theorem, you need negative real parts, don't you? What is this going to end up being? Now I have S squared is equal to minus 4. And this is why most people don't study electrical and computer engineering, because they get a little uncomfortable when this happens. When they say S squared equals minus 4? How do I square something and get a negative number? I don't know. Join me in class. What happens? It's not that magic, is it? Right? Where are those poles? Right on the imaginary axis. Can we apply the final value theorem? No. If you did apply the final value theorem, what kind of a result would you get? An incorrect result. It would say it's 0, but what's happening in the limit? Is z going to a final value? No, it might be bounded. It might be okay, but it's just continuing to shake. And what's it shaking at? What's its frequency? How fast is it shaking? What's its imaginary component? How far off the real axis is it? That's what influences how fast it's shaking. 2 radians per second, right? So you had poles at plus and minus 2, and you cannot apply the final value theorem to that. Now, I have plenty of time to talk about the initial value theorem. So again, we have if x of t and its derivative, x prime of t, are Laplace transformable, and now condition 2 is not so, what? Difficult? I mean, it might be difficult, but it's not as damaging as the last one. 2, if the limit as s goes to infinity of s capital X of s, now we're going to infinity with s and not 0. If the limit as s goes to infinity of s x of s, if that limit exists, then we can just use it. We can say that the limit as time goes back towards 0 from the right, that's why we're saying 0 plus, of little x of t is equal to the limit as s goes to 0 as s goes to infinity of s capital X of s. So, let's apply that. Suppose we look at example 1. Now we just have to have a limit. The limit has to exist. We don't have to check pole locations or anything because this is the starting value. Suppose capital V sub 0 of s is minus 4 over 2s squared plus 3s plus 1. We're assuming 1, it's well behaved. Now we want to look at the limit as t approaches 0 from the right. Whoops, and this is little v sub 0 of t. We're wanting to know where did we start. That's equal to the limit as s goes to infinity of s v sub 0 of s. The limit as s goes to infinity of minus 4s over 2s squared plus 3s plus 1, what's that going to? Now look at the highest powers in the numerator and denominator. I have a minus 4s and a 2s squared. It's effectively minus 2 over s, which is going to 0. So I started at 0, I bump around, and I go back to 0. That's the first example we had for the final value theorem. Now you have those theorems, you can solve all of your homework problems, I hope. Question? This material will be on next week's exam, yes. Oh, is today? No, you need to show up Tuesday because we might start going over this equivalence of the transforms.
I mean, I'm taking the exam right after class. It'll be real hard to learn stuff and then immediately be tested on it.
We'll be okay.